Hello and welcome to the Quantum BW Colloquium. My name is Manuel Hagelücken, and within quantum computing teams at Fraunhofer IA and IPA, I will guide you through today's colloquium. Quantum BW is the state initiative for quantum activities in Baden-Württemberg to pool all these competencies and to create an overarching umbrella brand that further strengthens these networks and makes them more visible. With this colloquium, we want to further promote the scientific exchange on quantum hardware and algorithmic topics in the field of quantum computing to present the latest developments in this research area and to promote the idea of co-development of quantum solutions. Today, I have the honor of introducing our speaker, Professor Dr. Sevag Gharibian from the University Paderborn. Professor Gharibian obtained his PhD in 2012 from the University of Waterloo in Canada under the supervision of Dr. Richard Klee. From 2013 to 14, he was a postdoctoral fellow in the group of Dr. Umesh Vazirani at the University of California, Berkeley. He was awarded Canada's top postdoctoral fellowship in 2013, the NSERC Banting Postdoctoral Fellowship, and was also a Simons Research Fellow at the Simons Institute for the Theory of Computing at UC Berkeley. Since 2018, he has been a faculty member in computer science at Paderborn University, Germany. He served from 2016 to 18 as secretary on the board of trustees on the Computational Complexity Conference, from 2023 to 24 on EATCS ICALP Steering Committee, and since 2016 is a founding editor of the open access journal Quantum. Good to have you here, Professor Gharibian. He will introduce us to on the complexity of many-body quantum systems, dequantizing the quantum singular value transformation, hardness and applications to quantum chemistry. Questions can be posted in the chat. With this being said, I hand over to you, Professor Gharibian.
Good. So thank you very much for inviting me and for the introduction. It is a pleasure to be here. I've only been to Stuttgart once, and that was on a negative note, is when Deutsche Bahn screwed up my journey, and I had to stay one night here. It almost happened again, because we were just coming into the city and we were told the whole station was shut down because of someone running on the tracks, but then that resolved very quickly. Anyway, so I'm here on a good note today. That makes me happy. My journey was stress-free. So this is a talk about, I'll try and be gentle, right? So how many people here are physicists? Yeah, computer science? Math? Okay, so mix as usual. I will start by giving you a gentle introduction to quantum complexity theory as we view it. And I'm always surprised at how much people are interested in that part of the talk the most, because they like to ask these basic questions that for me and nowadays, of course, are obvious. But so I always like to go through that first. And feel free to stop me at any time. Ask me any questions you have. I don't care how stupid they are. The stupider the question, the better. It's just easier to answer, right? So don't hesitate. So as a quantum complexity theorist, this is what we do all day, right? We like to view computational problems and think of them as animals that we want to characterize, right? They have different properties, they have different resources needed to solve them, and sometimes the problems we deal with are nice and fluffy and cute, like this one here. Sometimes they're quite scary, like the tiger, and sometimes they're just plain weird, right? Their categorization is really unexpected. And so, what do we do in complexity theory? What are we trying to do? Sorry, let me first give you an overview of the talk. So, like I said, first I'll take some time to really talk about the basics of how do we quantify complexity of a quantum system, or a computational problem. And then I'll give you a sense of just a quick overview of what are the types of many-body quantum physics problems we study in our group, and how do they kind of fit with this complexity theory. The bulk of the talk will be on this third part, which is, the little that I can say using complexity theory about quantum chemistry, I'll try to share. Okay, so let's start with how do we quantify the complexity of a computational problem? So how many people, by the way, are familiar with complexity theory at all? Okay, have you heard the word BQP? Probably, yeah, QMA? Okay, less heads? Okay, I'm going to go through that, okay? So computational complexity theory, just very, very basic, right? This is the question of, what resources do we need to solve a given computational problem? So time, space, qubits, for example, whatever it is, right? You can think of whatever you like. So that's the goal of this field as a whole. And so BQP, as you've probably heard, is the set of problems we like in quantum computing. These are the problems that we can provably solve efficiently on a quantum computer. Okay? And when I say solve efficiently, I really mean that for any instance of the problem you give me, I can solve it. Okay, so it's really a rigorous statement. And I'll define BQP rigorously in a second. And then we have the problems in what are known as QMA, which I'll also define shortly. This is like quantum NP. These are the problems where I don't necessarily know how to solve the problem efficiently, but at least, you can convince me of the answer if you give me a certain quantum state as what we call a proof. Okay? So you can sort of think of this as a quantum version of Sudoku, where Sudoku is very hard to solve, but if I show you how to fill out the puzzle, then it's very easy for you to check that it's solvable. But now instead of filling out a puzzle, you give me a quantum state, the quantum Sudoku. Okay, and the ones we dislike the most are the QMA complete problems, which are the subset of all these problems that we believe are basically intractable. There's no efficient algorithm for them, but of course we have no way of proving this using current techniques. And this is how you should view the world to first order, basically. So we have BQP, these are the problems we like, efficiently solvable. We've got QMA, which are the problems which include the ones we can solve, and ones we can't solve, but at least we know how to check the answer to, given a good proof. And here, sitting over here, are the bad boys or girls, right? These are the ones that are just believed difficult. So I'll define all this a bit more formally now, but any questions on this slide? Yeah?
I'm wondering how fixed are those relations?
We believe they're pretty fixed, but again, we can't prove anything.
Okay.
So we certainly don't believe any of these things collapse or coincide, other than what I've shown. Yeah?
When you say belief, is this just a collection of many instances of evidence, or is it like
yes,
a more rigorous framework where okay, such and such problem has to fit in this category?
It's more a collection of, well, we tried, but we don't know how to show it, kind of statements. Yeah, so it's analogous to how you have like P versus NP classically. This is a major open question for decades now, and nobody knows how to solve it. And we're kind of at the same place here. Okay. Yeah. So we would love to show that, obviously. That would be a breakthrough. Okay, good. Let me warn you right away, as a complexity theorist, typically we deal in idealized quantum computers. Okay, so I'm going to be clear, I'm not going to assume any noise in anything I do. Everything I do is perfect, platform independent, it's just math. Okay, so you can view me as an applied mathematician in many ways. And the other thing you always need to be careful of is most complexity results are worst case. And what that means basically is that it just shows that this problem is hard for some instances, but it could be that for most instances the problem is actually easy. Right? So you should need to keep this in mind. So even though something is hard in the worst case, heuristics might actually work very well in practice. So that's my disclaimer. Good. So let me give you a slightly more formal definition so you get used to like how I formalize things or how we formalize things in the field. So here's BQP, right? The class of problems we like. As computer scientists, we typically like to just turn everything into a yes or no question. So the answer is always yes or no. And we basically say that a problem with the answers yes or no is in BQP if there's what's called a uniformly generated circuit family. So just think of it as a polynomial-sized circuit. These are all just 1 and 2 qubit gates. And you take in your input to the problem, there's some n bits, and you get some workspace here, this ancilla. And you run the circuit, and you measure this single qubit, and you say, if it's a 1, that means that I think it's a yes instance, I'll accept the input. And if it's a no, if it's a 0, then I'll think it's a no instance, I'll reject the input. Okay, and the point is that if it was a yes input, then you should accept with high probability. And if it was a no input, then you should accept with very low probability. This is the idea. So you should see 1 with high probability or 0 with high probability. Then 2/3 and 1/3 are really not important. You can make that exponentially close to 1 and 0 if you want. Don't worry about that. Any questions about this slide? Yeah?
I was wondering about the uniformly generated.
Good. That's the one question
what do you mean by
you should ask.
Yeah.
Yes, so it's not enough to say that there's a magical polynomial-sized circuit out there that solves my problem. Because in order to run the circuit, I have to get my hands on the circuit first. I have to know how to come up with the circuit, right? And so this uniformly generated is that property. It says that not only does this small size circuit exist, but actually I can efficiently compute the circuit to begin with, like the sequence of gates I need to apply, I can figure that out. But it's a bit subtle. You look a little bit unhappy, but that is the short answer.
I'm not happy with the notion of uniform.
Yeah.
Like, what do we mean by uniform distribution in this context?
Oh, no. It has nothing to do with like uniform distribution or anything. If that's this just means that, okay, formally speaking, what it means is that you give me this input. There's a Turing machine, like a very basic classical computing model that you give me this input, and the Turing machine runs in polynomial time and outputs a description of the circuit. That's the formal definition. Is that better? Yeah, okay. I should have just said that to begin with. Yeah, okay. I try not to mention Turing machine. Okay, good. So most famous problem in BQP, as you probably know, is Shor's factoring algorithm. This is technically not in BQP because the answer is an integer, not yes or no, but it's very easy to turn it into a yes or no problem by just adding a threshold and asking if there's a factor smaller than or greater than, less or equal to, let's say, t. So this is all I want to say about BQP. So QMA, now quantum Merlin-Arthur, is almost the same thing. The only difference here, I've got it in red, is we have this extra register now where you can give me a quantum state, it can be any quantum state in the world, as a proof or a witness that's supposed to help me solve this problem. Okay? And so the way this is supposed to work now is that now if the answer to the problem is yes, then there should be a good proof you can give me to convince me that the answer is yes. This is still a poly-size computation. And of course, in the no case, if the answer is no, then regardless of what proof you give me, I shouldn't be convinced that the answer was yes. I really should reject it. So, this is kind of like a quantum bank machine in some sense. You put in your pin is correct, and it should accept. And if you're not who you say you are, any pin you put in should be rejected. Okay, so first, any questions about the definition? Yeah?
Is the verifiability hard for classical computers as well?
Say that again?
Is the verifiability hard for the classical computers as well?
What do you mean hard for the classical computer?
Like, if you give me the state, I can also verify if it's the solution.
Oh, so this is a quantum state, so we definitely need a quantum verifier for this. Like, the classical computer has no idea what to do with this. Yeah? Because I'm giving you this as a physical state. It might need an exponential sized quantum circuit to prepare, even. So that's the catch. Okay, does anyone know what the most famous problem in QMA is? The physicists certainly know it, they just don't call it what we call it, and study it like crazy people like we do. The so-called local Hamiltonian problem, which is, I give you a local Hamiltonian H, you tell me the ground state energy. Okay? I'm going to formalize this in a second. Okay, and here, of course, the proof you would give me is you just give me a copy of the ground state. This is why it's helpful to have a quantum state as a proof. So let me define the local Hamiltonian problem because I'm going to use that quite a bit in this talk. So here it is. So the problem is you give me a k local Hamiltonian H on n qubits. Okay, and here, I'm not assuming any geometric locality necessarily. It's just that the terms are all just act on k qubits at a time out of all n qubits. And you give me two thresholds for the energy, and they shouldn't be too close together because otherwise a quantum computer cannot distinguish those numbers. And your goal is just to tell me, if the ground state energy of this Hamiltonian is small, it's smaller than alpha, then output yes. And if it's large, then you should output no. Okay, so first, any questions about this formal statement for the problem? Okay, see, I told you know this problem. So, a classic example is something like the Heisenberg antiferromagnet, where you have, XX plus YY plus ZZ couplings, let's say on a 2D lattice or something. Good, and now the thing is that this local Hamiltonian problem, it's certainly in QMA, right? Because if you want to convince me that there is a state with low energy, well, the proof you would give me is a copy of the ground state. And then I could do like phase estimation or something and figure out the ground state energy and say, it's smaller than alpha. But it's not just that, it's actually QMA hard. And let me finally tell you a little bit about what I mean when I say something is hard. And I'm going to keep this very informal. So the complete problems of a class are, you should think of them as the strongest or the hardest problems in that class. So like, the lioness of the jungle. And what does that mean informally when I say that the local Hamiltonian problem is QMA hard? That means that if we go back to this thing here, this setup here, any problem of this form you give me, I can always massage it and make it look like an instance of this problem. So in other words, if you could solve this problem, then you can go back to the problem you started with, and you could tell me whether or not there was a good proof here or not. Answer the analogous question. So back here, that's what this says. So we can formally reduce any problem in QMA to an instance of local Hamiltonian. Okay. Now, of course, this does not mean local Hamiltonian problem is actually intractable because we cannot prove that PQP is not equal to QMA, right? But this means this is very strong evidence for us that it is going to be intractable because we strongly believe that you cannot solve like BQP and QMA are not the same, just like P and NP are not the same. But to be clear, we more or less don't actually prove anything. We just play a blame game where we say, okay, this problem, we don't know how to prove it's hard, so we'll prove that it's at least as hard as every other problem in QMA. And that is a good metric for us that this is hard. I think this is all I want to say about complexity theory. Any questions here? I won't really go through any reductions today. I'll just state some results there. I mean, there's a lot we know about this problem. The only things I'd like to mention is that the version of the problem that's QMA complete is when you want to figure out the ground state energy to within additive 1 over polynomial error in the size of your system. If you want very high precision, the problem gets harder. And if you want very low precision, this is the so-called quantum PCP theorem that you may have heard about. Well, conjecture that you may have heard about that nobody knows how to. Okay, so we don't know if the problem stays hard if you want very low precision. And this is kind of the area in which the work I'll talk about will touch on. Good. So this is the first part of the talk. Any questions? Okay. Good. So I'll briefly go over some of the areas that our group has studied over the last years, just to give you a sense of where we work. And if there's anything that interests you there, you can bug me after the talk. We can discuss. Yeah, that's the purpose of this section. So what are the kind of things one can say using complexity theory, right? And so the type of things we like to study are, so for example, simulating observables. So if I give you a Hamiltonian H, and now I'm not necessarily interested in the ground state energy, it's a more general problem. I want to know properties of your ground state, right? So I have some observable in mind, and I want you to figure out what is the expectation for a ground state. You could rigorously prove that this is a problem that's actually even harder than ground state energy estimation. It's complete for some funny class here. And I won't define that. So this is a pretty natural problem. You could think about things like energy barriers, like the kind of things you would see in the Torah code, for example. Like if you want to go from one code word to another, if you use a short circuit to do it, it's not possible because there will be a spike in energy at some point. And so, detecting if a Hamiltonian has this kind of energy barrier, this is also hard. Okay. Okay, a very basic question, given Hamiltonian H, is the ground state entangled or not? Also hard, obviously. And you see that you get different kind of funny classes coming out here. Like I said, it is a zoo, right? It really is a zoo, and one of those pictures I told you is the weird one, like this is the weird one. Like, this is a class by Francois Legal and others, which kind of, I think, went under the radar. It has a very funky definition at first glance, but it's really a great class, it turns out. And some of you might be interested in variation algorithms, and so the one work we've done here, for example, is everybody knows that at least intuitively depth minimization for these ansatz is hard. We can prove it formally now. So even for something like QAOA, which is a very simple ansatz, if you want to figure out what is the optimal depth to which you should run your ansatz to get kind of a good result out, this is really, really hard, even to do it approximately. Okay, so you will be nowhere near the right answer in general. But be careful, our results has nothing about constant depth ansatz. Okay, so we don't get hardness in that region. So if that interests you, you can ask me offline, yeah? Any questions here? Okay. And so a few works that are upcoming now. For anyone who submitted to QIP, you know exactly where this date comes from. Nowadays, there's this policy that a month after the submission to QIP, the full version has to be in the archive, but I think this is actually a really good policy. It effectively timestamps the papers. So one thing, these are the things we're starting to study if they interest you. So free energy, for example, which is in some sense a generalization of the ground state energy, but to higher temperatures now. So this is in that we give the first non-trivial upper bound for this. It looks like it's probably a harder problem than ground state energy, and this upper bound is that funny class I mentioned earlier. Something completely different for us is we started getting into like CV computation, like bosonic quantum computation. And here it turns out like more energy equals more computation power. This is the theme of the work. And you can do really ridiculous things, it turns out, with even polynomial time bosonic computations. If you pick like the right or the wrong gate set, you can solve like ridiculously hard problems, right? So which is a way of saying that, you know, these gate sets are probably not something you can implement in the lab with any sort of reasonable noise, okay? Because otherwise you do ridiculous things. So you can think of this as a no-go for certain gate sets in the lab. And finally, classical shadows is something that always also interested me. And here we can show, for example, that you know, this HKP protocol, which is a very, I think, famous shadow protocol, super simple. If I give you what I claim is something that I produced by measurement statistics from some state in a lab, and I want you to check that, am I lying or not? I can show that even for this, not I, but our team can show that even for this simple protocol, you know, this is a really hard problem. So these are things to come. Again, if they interest you, just ask me offline. I won't say anything more here. Any questions? Okay, good. So let me get to the main part of the talk then, which is what can quantum complexity theory say about quantum chemistry? And the honest answer is we can say something, but not a lot yet. And in particular, of course, one of the main things we all would like to see is some sort of separation of power between classical and quantum computers, right? When it comes to the task we care about, like quantum chemistry. And so, in this particular work, this was work with François Lagarde a few years ago. What did we do? Well, we talked to the quantum chemists, and we realized that they have a certain way of trying to solve for ground state energies, which is important to them for things like computing reaction rates. At least that's what I understand. You can correct me if I'm wrong. I'm going to bug you about that later, actually, because I need to understand that better. Good. And so we formalized this problem that they're solving in practice. And in practice, I'm waving my hands here. I'll say more later. They need to solve this problem to inverse polynomial precision in the size of your system. And so we first formalized this problem. It's some version of the local Hamiltonian problem. And we show two results. On the one hand, we say that if you want to solve this problem to a weaker precision than what the chemists want, then essentially you can dequantize this problem. You can solve it classically under these so-called sampling assumptions, which I'll say more about later. Okay, so if you want low precision, you're probably not going to prove something like this problem is BQP, which is the kind of thing we want to see. Now, conversely, we show that if the problem is in this precision regime we care about, it is going to be BQP hard, which means that we don't expect a classical simulation to work. So this is in some sense good news for quantum chemistry, but as usual, I always say you never trust what a quantum person says. You have to always read the asterisk on the result, right? And I'll tell you about the asterisks later. So this is a high level. Any questions here so far? This is what I'll go through. Good, so first let me define the problem we're going to study. So this was the local Hamiltonian problem I showed you before. And this is the kind of thing, like I said, that we as complexity theorists will study. This is really, really idealized. And we have our head in the clouds, but of course on Earth, real people are doing real work unlike us. And so how do they actually try and solve this problem, right? Because they have to figure out these ground state energies. And so one kind of popular approach seems to be, what you'll first do is use some sort of classical heuristics to, and nowadays there's quantum heuristics too, I believe, to try and find a good guiding state. What does that mean? That just means like, you can't figure out the ground state, but you find something that has some non-trivial overlap, at least with the ground state. Right? And as soon as you have that, you're in luck because quantum computers are really good at this game, right? Once you have this guiding state, and you want to figure out an eigenvalue of some operator, well, then you can just use phase estimation, at least on a large scale. Okay, and there are variational approaches too, but this is one of the things quantum computers are really, really good at. Okay? And so this is the process that we formalized into a computational problem. Okay, any questions on this slide? Okay. So here's the formal definition of the problem. It looks the same as the local Hamiltonian problem, except for what's in red. Okay, the only difference now is that now I'm going to assume that you have in your possession, you're lucky you found a good guiding state after all, some state psi. You don't have to check that it's a good guiding state. I'm even going to let you just assume it. And so you're promised that your overlap with the ground space is at least some delta, which you know ahead of time. Okay, and then now the question is, what is the complexity of this problem? Okay, so this is kind of the second half of what the chemists like to do. Okay, first, any questions about the definition? Okay, so especially computer scientists in the room might be really upset with me saying this because, what do we mean by representation of a n-qubit quantum state? You can't write this down classically, right? So in this work, it suffices to use two representations. So first, we'll consider the sampling axis representation, which I'll define later. And using this kind of representation, we can show that if you only care about that low precision regime, like constant, this is a classically solvable problem. And the regime which chemists are more inclined to care about, this 1 over poly, right? For that, we get this BQB hardness, and here we use a really, really, really simple class ansatz here. So even with like these very simple types of guiding states, it's already going to be something only a quantum computer can do. And I'll define both those things in a second. Okay, so just to put everything together before I go forward, basically, this GLH, what we can show here is that this problem with high precision is hard for quantum computers, meaning that only quantum computers should be able to do it. We certainly know that the problem is in BQP because given the guiding state, you can run phase estimation, and so you can solve this GLH. And so it seems like this problem, with that precision that chemists might care about, perfectly characterizes the power of quantum computers. Okay, and the only thing I want to mention here is that you should distinguish this result from things like quantum advantage, like random circuit sampling or Gaussian boson sampling. Those results are average case, so they're arguably stronger hardness results because it works even if I pick an instance at random. Whereas this result is like BQP hardness, which is a worst case result. So it just means that out there in the wild, there are some instances which are BQP hard. Doesn't mean the average one is hard. Okay? That's just my, again, like I said, always be careful with the STOC asterisks on any quantum result, so this is one asterisk. Okay, so I won't prove this result, I'll just state it for you. So first let's talk about the hardness result. What exactly do we show? So here's the guided local Hamiltonian problem again. You get some guiding state here, and the class of the ansatz for guiding states we need here is what we call a semi-classical state, and it's like one of the simplest states you could possibly think of. Basically, it says, pick your favorite set S of strings. That's only polynomial size, so you can write this down. And you take what's called the subset state, which is just give me an equal superposition over those strings. That's it. So you can certainly write this down classically using polynomially many bits. Yeah, there's like no magic here at all. It's just a very simple class of states. Any questions about what this means? Good. So this is the class of states we'll use, and the result we show basically is that for any overlap, so the guiding state has some overlap, right? So even if the overlap is very, very high, so even if the overlap is inverse polynomially close to 1 with your ground state, this problem is still BQP hard. Like a classical computer still can't do it, basically. And additionally, this is true even if your H is, physically motivated in the sense that maybe it's like the two-local antiferromagnetic Heisenberg model, for example. And we can also show that it's hard even if you are not just interested in the lowest energy, but any of the first like polynomially many energy levels. Okay? And by hard, remember, it doesn't actually mean it's hard, it's BQP hard, which means quantum computer. We know how to do a quantum. It's just hard for a classical computer. Okay, now, here's the next asterisk. Okay, whenever I give this talk, I sometimes get this question. It's a very good question. As far as I'm aware, chemists actually care about 1 over n precision in the system size. So if you think about your Hamiltonian as having norm 1, and you have n sites, then you want like 1 over n site, 1 over n precision, is what I'm told at least. And the hardness we get, in order to get this BQP hardness, we have to ask for actually smaller precision. We have to ask for something like 1 over n squared. And this is just because some of the tools we have in complexity theory, like nobody knows how to encode hard problems into this precision yet. This is just not known. So it's entirely possible that something funny happens at the precision that chemists actually care about. We don't quite get there. Okay? Again, as far as I'm aware. Yeah.
So the delta, the overlap,
yeah,
that is actually corresponding to the 1 over n square precision.
No. That's completely different. Yeah. This is just about the overlap with the ground state. This is just saying to what precision do you want to figure out the ground state energy?
Yeah, that's BQP hard because you're going for 1 over n squared.
Yes, exactly. If I ask for like this gap between alpha and beta, if I ask for this to scale like 1 over n instead of 1 over n squared, we don't know how to prove hardness. And that's not just like our problem, that's all of complexity theory's problem in the sense that it's actually one of the fundamental roadblocks. We just don't know how to get to that level of precision when we talk about the local Hamiltonian. So, I retrust to quantum first. Questions otherwise? Okay, so then I'll tell you a bit about the classical, the quantization result. This is in high precision, so it's again not the regime for chemists so much, but how much time do I have just so I have a sense? My pacing?
45, I think. You have 10 minutes something.
10 minutes? Okay, so I'll try and do this somewhat a bit quicker, yeah. Okay, good. So in this setting, basically, we just want to show that when you want a weaker precision, you can solve the problem efficiently. We'll need a different type of guiding state. And it's what's called a sampleable guiding state. And this is a standard definition now in the field when you talk about any of the dequantization results. It's basically a definition that comes from 20 years ago from like classical recognized linear algebra. And the main things you need to know, maybe as a physicist, is essentially what we assume about the state. Is that we assume that there's some classical Turing machine or some classical computer that you give me an index I of the state, and I can tell you the amplitude at that state efficiently, number one, so I have query access. And this one essentially says I can measure the state in the standard basis. I can simulate sampling according to that distribution. And the reason why you want this one, just so you understand, is that this alone, like, what the hell good is this, right? I have this giant vector, 2 to the n slots. So fine, I can query them one at a time, the entries, but I have no idea which are the most important entries in some sense, right? The biggest entries. So I only have polytime, so this allows me to zoom in on the most important entries, because if you measure in the standard basis, you'll see with higher probability the indices that have the highest weight. This is essentially why this is so helpful. I don't need to talk about this. Okay, so we can compute entries of the vector efficiently, and we can essentially measure this thing in the standard basis and produce, like, sample according to that distribution. Any questions about this? So the main theorem we show here is that if you're only interested in constant precision, then, and assuming you have like a guiding state which has this sampleable form, then you could solve this problem efficiently. And to do this, there's a sequence of steps that goes into it, and I probably won't get into it in the interest of time. But basically, it boils down to solving this quantum singular value transform classically when you only want low precision. This is really what it boils down to. Okay, so how many people have heard of the QSVT before? It's kind of like this, the mother of all quantum algorithms in some sense. It captures a lot of what we can already do in quantum algorithms. So basically anything you want to do that is quantum linear algebra, so inverting matrices, simulating matrices like e to the IH, et cetera, a lot of that can be recaptured just in this one framework. And so this is why this is nice that we can dequantize this one framework in one shot when you want constant precision. The other time we know how to dequantize that framework, not we, but the field, is when the matrices involved are low rank, like you might see in machine learning. Okay, so I won't say too much here, what do I want to say in the interest of time? So maybe I'll give you a flavor of how the proof works. But basically, what does it mean to dequantize the QSVT for us? It basically means that there's some sort of like inner product thing I want to classically approximate. So basically, you have some starting vector, and then you want to apply some polynomial of the absolute value of the matrix A. This is the singular value transform, and then you want to compute the overlap with some B here. And essentially speaking, like the point here is that we can approximate this thing classically, as long as you don't want high precision. And the way you do it is actually very, very simple. You just use the fact that what you're staring at here is just an inner product between some V and this matrix here. And V is the one we have sampling access to. That's the guiding state. And so what we do is we repeat this over and over again. We first say, I'm computing an inner product. This is a giant exponential sum over many things. So first tell me what are the important indices in that giant sum for me to focus on. So that's why we need the sampling access in V. So give me an index that has high weight. Once I have that, I can use that query access to compute the actual entry in Vj. And so now in this inner product, I know Vj on the left side, and so I need to compute the jth entry on the right. So I can add it to my sum. And this you can do. This takes a bit more work. But because we're assuming the matrix A is sparse, which is a standard assumption because otherwise we can't even do Hamiltonian simulation, you can actually compute the jth entry of the right-hand side here. This we can do. Okay, I won't see more. And now you're done because you can compute the product of the jth term on both sides, so you add them to your running total. You have to renormalize, of course, because I'm subsampling. I'm not going through the entire sum. But you can prove then that this will give you a good bound. Okay, if you just want a constant precision. Okay, I won't say more about that, but are there any questions? That was certainly a bit fast.
You said that sparsity is necessary, but also for the quantum.
Yeah, sparsity is necessary for both algorithms. Like, so the classical algorithm here definitely needs a sparsity to be able to compute this jth entry of this thing. But even quantumly, like you can't do anything with a non-sparse matrix typically, because we can't even do like Hamiltonian simulation. So
it's all about the precision. You mentioned it already. All about the precision that quantum can do better.
That's what it seems like. That seems to be the dividing line, at least when it comes to this like guided local quantum. Absolutely. Okay. So I'm not going to get into that. So of course the main open question here, let me pretend I'm a quantum chemist for a few minutes, is of course, is there a chemical model for which we can find a guiding state efficiently? Right? I mean, and this is like a huge open question. This is not just me asking it, right? This is what everybody wants to do. And so just some very naive observations from a complexity theorist regarding this, right? So first of all, of course, because we know that solving for ground state energies in general is QMA hard, we should certainly not look for a general algorithm that works for an arbitrary Hamiltonian. This is just not going to happen. Right? But again, there are holes in the arguments we have. So for example, the Heisenberg antiferromagnet, which is, to my understanding, some sort of toy model for quantum chemistry you guys like to play with, even though it's still bloody hard. We can prove this thing is QMA hard as well to figure out the ground state energy, except we don't know how to do it in the case you actually care about, which is when you have unit weights on all the local terms. We don't know how to show hardness then. So it's entirely plausible that when you have unit weights like you actually would play with as a physicist, that this becomes easier. Okay? But so typically you want to think about the properties of the specific Hamiltonians in play. Okay? Don't do anything too general purpose. Our biggest problem as a field, as you probably know, is that quantum computers are tasked with doing very great things, right? We have to solve things exponentially faster than any classical computer, otherwise it's interesting, but it's not as interesting, let's say. You know? And so what you have to do, therefore, is you need to find like some sort of chemical model or some computational problem, which is not NP hard, because we certainly believe quantum computers cannot solve NP hard problems. So if you can prove your problem is NP hard, you need to go finer and be more specific about your model. But yet the problem should not be known to be efficiently solvable classically. So there's a very kind of thin needle you have to thread. And we give these problems a name. They're called NP intermediate. They're rare, and it still blows my mind to this day that factoring is the one that fit the needle that also came into BQP. Like this is just, a rare stroke of luck as far as I'm concerned. Okay. Of course, the problem is we have no way of proving a problem is NP intermediate. But if you want an exponential advantage, this is the kind of thing you're looking for, right? It's got to be not NP hard, but not obviously efficiently solvable classically. This is the hard part. So the other thing you need to keep in mind is heuristics, right? So some problems which are NP hard, like the satisfiability problem, which is the classical version of the local Hamiltonian problem, it's notorious for being easily solvable in practice. Meaning for most instances you could care about, you can solve it quickly. And in fact, their entire conference is dedicated just to that. Every year they try and beat the last person's record, okay? And a great example of this in today's life is, of course, machine learning, which does pretty poorly on certain inputs, but on average, for specific tasks, it does tend to do pretty good, right? But good luck trying to prove that it actually does good, right? This is just heuristic. And of course, the big problem we have here is that, if we're trying to run heuristics rather than some efficient algorithm, well, we can't run our quantum algorithms on a large scale yet. This is the huge issue we have right now. Right? So I feel your pain there, for sure. Good, I think that is all I want to say here. Any questions? Okay. Good, one thing I mentioned earlier, in case anybody has insight, is, so here's an example, the hardness of the electronic structure problem from quantum chemistry. We know, for example, that if I pick a single particle basis, which is completely artificial, you can show that this problem is hard. But of course, it would be nice to do this for chemically accurate, chemically relevant single particle bases. And so this is the kind of divide we have right now in trying to understand quantum chemistry with complexity theory. So when I talk to my chemistry friends, I'm like, okay, tell me what is a meaningful single particle basis for you guys, so I can study that. And they say, sure, no problem. They give me a giant database of like 400 bases, all specified as a giant table of numbers, right? And I'm like, what the hell am I going to do with this, right? Like, I'm a theorist, I need equations, right? I need something analytic. And so there's a huge divide, and if you have any background in this, I would really like to talk to try and bridge that divide. Good, so summary, complexity theory generally is aiming to characterize resources required to solve computational problems. BQP for us is good, it's what we can solve on a quantum computer, at least on a large scale. QMA is also good, we can verify them. QMA complete is bad because we don't think we can solve them efficiently. And as I mentioned, there are many problems in many body systems that you can try and understand with complexity theory. And one of the main ones I think much of the field is interested in is quantum chemistry. Good, thank you very much for your attention.
So thank you so much for this great presentation. Are there any questions?
If you have a local Hamiltonian problem, I would say the worst case imaginable would be just random couplings, everything, all coefficients are random.
Yeah.
What would be an average case which we can study? Because you also said that if you would have just an antiferromagnet, magnet, it's still hard.
Yeah. Well, okay, so random couplings, they're actually easier to study in many ways, in the sense that, like, when you think about random SAT, and now there's been like various papers on like this SYK model and things like this, like Hastings and O'Donnell, for example, where when you have the randomness actually helps you in the analysis, and we have things called like this, like phase transition threshold, where when you look at the ratio of clauses to variables, for example, if there are constraints to qubits, let's say, if there are very few constraints relative to the number of qubits, one can prove typically that the system is always satisfiable. There's always going to be like a low energy state. And then there's some middle point, there's some transition point where it gets very hard when the ratio between constraints and variables is just right. Then it seems to be very hard, the problem. And then when you have way too many clauses for the number of variables, of course, then you know that there is no low energy state because there are just way too many constraints. Like, so you have this phase transition. And so I would be wary of saying that it would be harder in the randomized setting, because there sometimes we can prove more, if you will. But in terms of like an average case, I don't think I have a good answer to that otherwise, right? I mean, I'm not sure how to think about things like the Heisenberg model, let's say, in a randomized setting. I mean, typically my understanding is the couplings are fixed also to some geometry too on top of that, right? So we presumably have to look at something like the SYK model, which by definition is randomized. I don't know if that helps.
So what does this phase transition, how is it characterized? There's some kind of value or something which you could look at?
Yeah, essentially. So there's some like, you look at the ratio between the number of constraints, interaction terms, to the number of qubits. That's like some number. And so when the number hits a certain point that we have no idea, right, the problem tends to get hard. And that's kind of where the hardness of the model lies. Because if you get far away from that point, it's not difficult to prove that, with super high probability over the choice of constraints, the problem will either be almost always satisfiable or almost always not satisfiable. So it becomes a lot easier to answer yes or no in those regimes. So I would encourage you to look at papers like the Hastings-O'Donnell paper, which are really good. I think they were studying like Gaussian states as an ansatz for this SYK model, and when they actually do a good job at doing approximations, and so that was quite neat.
I saw that.
Yeah, exactly.
Any more?
Is there any practical scenario where O of 1 precision is already enough for us?
So practical, I'm sorry, you want a practical scenario where O of 1 precision?
Like, let's say we are solving a specific Hamiltonian, and I'm satisfied with O of 1 precision.
Oh, and you want, okay.
Because like,
So you mean like
is O of 1 precision already enough for me to say, okay, I think this is fine, we don't need to do quantum algebra?
Yeah, you mean so like a chemically relevant one?
Yeah,
Yeah, I think that's your job to tell me. No, I don't know. I really don't. Yeah. So whenever I talk to chemists, yeah, they say they want that 1 over n precision. Or if the Hamiltonian is not normalized, it's got to be constant, but then the norm of the Hamiltonian is polynomial in that case. Scales like n. So unfortunately, I don't know.
or is there a measure how far we are away from the true solution of that problem if we are already at O of 1?
What do you mean? Oh, yeah, I don't have a good feeling for this, to be honest. Like my understanding, for example, for things like reaction rates is you guys want to, you don't actually really care about the ground state energy per se. You want a couple of low energy values, and then you kind of subtract them. You do some sort of difference trick, and then, so, but that sounds like you want sufficient precision so that these differences start to make sense, right? And so, I mean, naively, it feels like constant precision is going to be pretty bad for that application at least. But again, I'm not a quantum chemist by any means. So. Go ahead.
Currently, there are many things a classical computer still has to do, like computing the gate setup for the Hamiltonian.
Yeah.
Will there be is there some approach to get the Hamiltonian on a quantum computer? Because it also scales exponentially, so this is a huge bottleneck.
So, sorry, let me sharpen your question. So, yeah, so if I want to run a quantum algorithm, yeah, I typically need a classical computer first to compute the circuit to begin with. And so what do you mean by get a Hamiltonian on a quantum computer? Just to be clear, what are you looking for?
Just the setup of the gates.
But okay, but you're not talking about a circuit, you're talking about a Hamiltonian.
Yes.
So, but, so what's the relationship between the Hamiltonian and the circuit in your question?
Just how to make the measurement correctly.
Oh, you mean like of energy or something?
Yes.
I mean, I'm not aware. I mean, it sounds like you're asking, is there some quantum way to come up with the circuit itself? Is that what you're asking? Yeah, I'm not aware of anything like that. But, you know, to be fair, this whole field of like quantum compilation and software engineering is completely outside my purview, to be very fair. So I can't answer for what those very intelligent people are doing.
So you talked about some of the previous words, and you said something about ground state entanglement in your slide. Could you tell us more what you worked on?
Oh yeah, sure.
estimate what kind of entanglement is existing in a given problem, or?
Yeah, so we were working in like the simplest version of the problem, which is I think of a cut, you know the cut, I tell you the cut ahead of time between like the qubits, so there's like an A and a B subsystem, and your goal is to estimate the entanglement entropy across that cut essentially in the ground state.
So it's a bipartite.
Yes, that's right, yeah. So, and there we can get various results depending on, it turns out to be, okay, it's not, we can't yet say if one is easier than the other, but basically if I'm asking, is there a low entanglement state, that seems to be a different computational question versus is there a high entanglement state? Because complexity theoretically we get different classes, and the problem is we have no idea what the relationship between those two classes is yet, but they seem to have different complexities. There are other papers that, I think we're the only ones who have studied this from a complexity theoretic perspective, like using QMA, etc. But there have been some other nice papers that study like pseudo-random quantum states, and they study similar questions, but they can fine-grain the question a lot more. They can talk about like area law versus like volume law entanglement and things like this. But there the setup is different. It's not that I'm giving you a single Hamiltonian and I'm saying, you know, tell me about this Hamiltonian's ground state. There it's like I have a family of Hamiltonians and I pick one at random, and then for you on average to tell me about that Hamiltonian's ground state becomes what's called LWE hard. It's hard for this problem called learning with errors. So the setting is different. You're not talking about one fixed Hamiltonian. But if you care about that kind of more fine-grained volume law versus area law, that is seems to be the more appropriate place to look.
There is this funny result in learning theory that given a quantum circuit, to compute its output is computationally hard.
Yeah.
But when I want to learn its output, it is easy, except when there is one T-gate involved.
Oh yeah, okay.
I'm talking about this funny result. Is there like a similar result in complexity theory with respect to like some Hamiltonians that?
Yeah, so there is actually one result that I really like. We tried to build on this, but we didn't succeed. There's a result by, I think, I'm not going to remember all the authors, but Sergey is on it, Sergey Bromby, Chinmay Narka is on it, and a few others. And basically, they study a similar question. You imagine like you have QMA, but now you say, okay, my verification circuit has a limited number of T-gates in it. And what happens then? Like, let's say you have one T-gate, right? So in the extreme case, if you have no T-gates, you can argue that basically you don't really need a proof. It just becomes like a stabilizer computation. And that's kind of long been known. But they basically show that if you have k T-gates, then you can compress the proof you need down to dimension 2 to the k. So in other words, if your verifier only has a logarithmic number of T-gates, you don't need a proof at all. It just becomes a polynomial dimension space now, and then you can just get rid of the proof altogether. So that's the only result I'm aware of. I really like that result. But yeah, we were not able to extend that, let's say, in any reasonable way. It's a good question.
Any more questions?
So if you have some QSVT circuit
Yeah.
for, I don't know, Hamiltonian simulation or matrix inversion,
Yeah.
how can you characterize if there is some potential non-trivial speedup against classical? Like, is it the degree of the polynomial? Is it the input? Is it the axis model or the state input? Where would you say is the?
So okay. So first, I don't think that has a clean answer. That seems it's very difficult to answer the general questions of the form. You know, where does the speedup come from? Let's say. Typically. Okay, so all of these, typically QSVT problems are all exponential sized linear algebra problems, right? So you're inverting a matrix, exponentiating it, whatever, right? So you want to think about tools where, settings in which classical algorithms, you know, can kind of do just as well, at least with some additional assumptions, typically like sampling assumptions. And these tools come from various fields. Typically, they're not necessarily new tools like the tools we use or the dequantization works. They typically use things like tools from randomized linear algebra, which have long been known. Like if I have like two matrices, right, and I want to verify their product, it turns out I don't need to do the full multiplication. If I have sampling access, it's long been known that I can randomly pick some rows and columns and approximate the product very quickly, for example. So those are the kind of things you want to watch out for. I don't think I have a cleaner answer than that in terms of, say, the degree of the polynomial or anything like this. I mean, typically I think that depends very much on the problem you're trying to solve, right? And for us, the degree was very important because okay, good. So maybe this helps answers your question a little bit better. In our setting, if you only wanted constant precision, right, we can only tolerate a constant degree polynomial in your QSVT application, you know? Because the runtime was going to be exponential in the degree of the polynomial. And the degree of the polynomial turns out to be very closely related to the precision you're asking for. You know? So indeed, in that case, like if you have a constant degree polynomial, you can dequantize it. If not, our algorithm, you know, it still works, just not polytime anymore. So fine, I agree that maybe that's one place you can focus on. I agree. Yeah, I don't think I have a better answer than that.
I have one of those stupid questions, if possible.
That's good.
So how do you prove hardness? Reducing to a known hard case?
You mean in general?
Just
yeah?
in principle, yeah, just in general.
Okay, so there's various ways to do it. You can either start with the most basic way to do it, which is typically harder, is you can just start with an arbitrary QMA verification circuit, or let's just talk BQP. It doesn't really matter. There's some quantum circuit. Let's talk about a BQP circuit, right? So I have some poly-size quantum circuit, and I want to take its output distribution on that qubit, and I want to embed it into some other problem. Okay, so for example, like solving linear systems of equations. That's inverting linear systems is like known to be a BQP complete problem. And so how do you do this? Well, you have to take this circuit, right? And then you have to play with it, like massage it until it looks like some matrix you want to invert. So that if I invert that matrix and measure the result, then I can recover the output distribution on that BQP circuit. This is roughly what you want to do in this particular case. Yeah? And then how you actually do the embedding now is really context specific, right? So there's no kind of fixed algorithm. The way you do it for matrix inversion is you take your BQP circuit, you essentially use these kind of old school techniques due to Feynman about like clock constructions, and you show how to, you build one magic unitary that every time you raise this unitary to the next power, it will apply the next gate in your circuit, basically. So it kind of encodes your original circuit, but in this very simple manner where you just keep raising this thing to higher and higher powers, and it just applies more and more of the circuit. And the reason why you like that is now you take the Taylor series expansion of the inverse function, and that is just like something that goes off to powers of this unitary to infinity. And so you can recover the action of your circuit by thinking about this Taylor series now. Very roughly the idea. You know? I don't know if that helps or hurts, but this is the basic thing, and it requires creativity, right? There's, unfortunately, well, fortunately or unfortunately, it's not clear how to do this yet with AI or something.
Okay, then thank you for your questions. Thank you for this great talk. If there are more questions, feel free to ask afterwards. In our next colloquium on October the 16th, we will have Dr. Vadim Vorobyov from the University of Stuttgart on site presenting his work on quantum sensing. Thanks for your attention. Have a nice afternoon.